In this video, we'll discuss some extensions of the standard restricted Boltzmann machine. So we've seen the basic restricted Boltzmann machine, and there are two things that makes the restricted Boltzmann machine basic. The first is that we have only considered binary visible units, and so we'll talk a little bit more about whether we can extend it to other types of observation. And the other part of it is the fact that it's restricted. That is, we are not allowing for connections between either the elements in the visible layers or the elements in the hidden layers. So we also talk about what happens when a Boltzmann machine is not restricted. So first, a generalization to other observations. One particular observation type that we'd like to be able to support is unbounded reals, so values between minus infinite to plus infinite. And it turns out that there's an extension known as the Gaussian Bernoulli that allows to model real-valued observations. And the extension is actually fairly straightforward to obtain. All it requires is that we add a quadratic term into the energy function, and the quadratic term needs to be positive. So here we have the quadratic term in question. If we do this, then the only thing that this is changing is actually the definition or the corresponding conditional distribution P of x given h. That's because we've added a term that only depends on x. So it's a constant if we were to compute P of h given x. And actually what this is going to yield is a Gaussian distribution, which is such that its conditional mean is going to be just a linear transformation of the hidden layer. And the covariance matrix is actually going to be an identity covariance matrix. So we have a variance of 1 over each element of x, a conditional variance of 1 given the hidden layer, and no correlation between the elements in the matrix. There's a variant which is a bit more involved, where we can actually play with and model the conditional covariance matrix. I encourage you to look at the literature for more details on this, but very simple thing to do to, in a sense, avoid having to do this is to just normalize the training set by first subtracting the mean. So this just will allow us to make it easier to not have to learn the mean of the average value of the inputs, and then to sort of standardize it in terms of its covariance structure. Then we could just divide each of the input by its training set standard deviation. So if we do this, then it tends to be easier to learn this Gaussian Bernoulli RBM, and it tends also to be a bit less important to learn the conditional covariance or the conditional variance of each element in the input vector. Still, it's a model that is still a bit harder to train than a regular RBM. In particular, in practice, unless we use a usually smaller learning rate than what we use for the standard RBM, we tend to find sometimes that training can diverge. So you have to be a bit more careful in the selection of the learning rate. But still, it's still the fact that this is a valid model for real valued observations, and it's been used by some with success to learn good features from real valued vectors. It will learn different features. So if we train it on the MNIST dataset, this is an example of what you can get. We do get our sort of pen stroke detectors like hidden units. Other features here are harder to interpret. You can get more meaningful features by introducing some sparsity in the hidden layer. You can consult the course website for literature on that. But I'm just showing this really to illustrate the fact that you will get different features if you use, say, a Gaussian Bernoulli RBM than if you use a regular RBM. And then there exist extensions for other types of observations, for instance, binomial observations. So an observation between 0 and an integer, say n. So you can look at this paper for more about that. This can be useful in this case if you want to actually model explicitly the integer valued intensity of pixels instead of treating it as either a binary value or a real valued value. For modeling multinomial observations, so for instance, words in text, I give you two references here. There are certain challenges related to modeling words, which are related to the fact that words are intrinsically very high dimensional objects. They can come from very large vocabulary, and so these two papers are examples of papers that try to deal with this difficulty. And I encourage you to look at the course website to get more papers on other types of variants for modeling different types of observations. And in particular, for modeling real valued data, there are other more sophisticated extensions of the RBM, which, for instance, for modeling pixels, can actually perform better than the Gaussian Bernoulli RBM in its basic form as I've described it. And finally, what about if we make a restricted Boltzmann machine non-restricted? In fact, originally the Boltzmann machine was proposed, and it's only later that the restricted variant was proposed, highlighting the fact that if we didn't have connections between the hidden layer and the visible layer, then certain things became much more efficiently, certain computations were much more efficient. For instance, we get some interesting conditional independence between layers. But in the original Boltzmann machine, you would have connections between the input elements, so that would allow us to model direct dependencies between elements in the input vector, and we do this by adding this term in the energy function. So we'd have a matrix which would model our preference between the values of pairs of input elements in the input vector, and then we could have, again, such connections by adding a term like this in the energy function, which would allow us to model directly the dependencies between hidden units and have certain types of interaction patterns, inhibition and excitation patterns between the hidden units. And sometimes we can actually use just one and not the other, in which case we'd talk about a semi-restricted Boltzmann machine. So this would be a Boltzmann machine, for instance. We could decide to remove those and only have interactions between the hidden units. In this case, the visible layer would be conditionally, each element in the visible layer would be conditionally independent given the hidden unit, but it would not be true the other way around. There's been some papers that have shown that for modeling natural image patches, removing this but only maintaining these connections can be beneficial. So again, there's a lot of literature on trying to actually try to incorporate these types of interactions between either hidden units or visible units. I encourage you to look at the literature in the by Googling different papers on Boltzmann machine. The main thing to remember is that if we do introduce these interactions, perhaps we have a more powerful model, but it's much harder to train, because if we want to do contrasted divergence, for instance, sampling from this model, performing Gibbs sampling, now requires that we update each element in our undirected graphical model individually given the others, because now we don't have the nice conditional independence property that we have in the restricted Boltzmann machine. So for that reason, this model, the full Boltzmann machine, is not as popular as the restricted Boltzmann machine.